So typically I give these kind of talks in front of a cryptographer audience, and they get impressed by the cloud native stuff. Maybe this time it's the other way around, let's see. So maybe some words about me. So I have been a research engineer for a lot of years. Now I'm more into project management and leading people, but still I enjoy technical stuff a lot, and I'm one of the maintainers of this Carbyne Stack open source project that I'm talking today about. It's one instance of another pet, so we heard about pets already today, but this is a different pet. It's privacy enhancing technologies, and Carbyne Stack is an implementation, a cloud native implementation of one of these privacy enhancing technologies. So I'm working for Bosch. Most of you probably know Bosch, maybe for its automotive components that we sell, maybe for the fridges, maybe for some tools. But we are also working a lot with IoT, with digital systems in general, and they're protecting the privacy of our customers, protecting IP in collaboration with our business partners plays a very important role. And that's the reason why we are looking into privacy enhancing technologies. I'm specifically working for Bosch Research. We are headquartered near Stuttgart in south of Germany. We are roughly 1,700 people looking into various topics in all these different domains that you can see here on the right. And I'm specifically working in the ICT domain. So I guess most of you have not heard about secure multi-party computation before, so I will give a brief overview on that, very brief. It's somehow related in a sense to confidential computing because it gives similar guarantees, but on a different basis. We will get to that soon. But here's the 101. So secure multi-party computation enables a group of people running infrastructure that allows them to work on data while it is encrypted all the time. So you know TLS for encryption in transit, you know modern databases provide encryption at rest, and this is closing the gap in the sense that it provides encryption in use. So even while processing the data, it never gets decrypted. It's also a subtle difference to what we heard about confidential computing, but also more on this in a second. So the guarantee is that here in this case, Alice and Bob, they can spawn Carbyne Stack clusters. These are basically implementations of MPC protocols and orchestration logic around it. And they can input their data on their local infrastructure, on their local running Carbyne Stack instance, and can be sure that during the processing, the other party, and there can also be more than two, will never see the input data that they provided to this computation. So that's the basic guarantee. And it's enabled by cryptography, not by hardware protection mechanisms as for confidential computing, but by cryptographic protocols and associated distributed computing protocols. And what we do with Carbyne Stack is we combine these secure multi-party computation cryptographic protocols with cloud-native technology. And that's the reason why I'm here today to talk about this topic. Why we do this? Because we have seen a lot of progress in improving the efficiency of secure multi-party computation protocols over the last decade, basically. But what is missing today is how to deploy that stuff, right? And that's something that we are interested from Bosch Research point of view because our business units are interested in it. And because it's a huge task to combine these two technologies, we decided to make this an open source project and try to find collaborators, other mainly big companies that join in the effort and implement that stuff with us together with the goal to, as I said, enable enterprise-grade deployment of these technologies. So I will talk about both aspects here at the bottom of the screen, enterprise-grade and always encrypted, a little bit more in the rest of the talk. So now it gets a little bit scary. I will promise you we will skip a lot of this, but just to give you an impression of how things work. So here you can look on the right on this fancy graph here. You have three parties, and what they want to do is all of them have a secret value, right? These are the red circles here, the numbers in these red circles. And what they want to do is they want to jointly compute the sum of these numbers without giving these numbers to the other parties. And how this works is they use a technique called secret sharing. So they take their number, for player 1, this is the 7, and they split it up into a set of numbers that together sum up to the original secret. So the 7 is divided in 1, 2, and 4. And the same is done by the other players for their own secret. And then this actual secret sharing happens. So they send one of these shares. So player 1 keeps the 1 for himself, sends the 2 to player 2, and sends the 4 to player 3. So that means they get some, let's say, part of the secret, but they cannot reconstruct it. When they only have the 2, they cannot conclude that it has been a 7 at some point in time. They would need to collect all the secret shares and recombine it to get the secret. And then that's the nice property of this secret sharing. It's additively homomorphic. That means they can do the computation of the sum locally on their secret shares. So what these guys now do, they take the secret shares that they got and sum it up. So player 1 has received 1, a 0, and a 2, and this sums up to 3. And the same is done by the others. And then they have, although you can not see it at the moment, they have already done the summation of the secrets, because when they now, that is called the opening process, when now they open the locally computed sum to the others, you can see that if you sum up, everybody has the same in the end, and if you sum that up, 3 plus 10 plus 7 is 20, and if you look at the top, that is exactly the sum of the secrets that you had before. So that is super simplistic. That's just addition. It's very easy. We will not go through that. That's now the same kind of explanation for doing multiplications. The takeaway is twofold here. So first of all, with addition and multiplication, you can basically implement every program, if you combine it with a branching instruction, that is out there. So it's Turing complete in that sense. And it's, as you have seen in the other slide, it's not a typical architecture because you have multiple parties collaborating and they communicate a lot. And that's the reason why these systems are very different from what you know when you do computation in a single place, may be protected by confidential computing or not. It's here a distributed, decentralized system, and that's the difference between this and standard systems. So what we get here is now what you can see here on the right, this nice little figure. So you can get here, in that case, 3 parties. They can together implement what we call a virtual cloud. That's the thing in the middle, by deploying a Carbyne Stack instance and then engaging in a so-called binding process where they create some cryptographic material. That's the key in the middle of that cloud that is shared among the parties, and nobody can reconstruct that key. And using this mechanism, they can create this virtual cloud that then exposes services that you are used to from normal cloud offerings, services for storing data, and services for computing on that data. So in the second step, after the cloud has been established, every party can provide their inputs into the virtual cloud. Then using secure multiparty computation happens on top of that data. And at the end, maybe for some statistical aggregation that you do, you send back then a chart of the statistical distribution of the input that has been provided to the parties. So what you get is this always encrypted collaboration substrate, as we call it. So a means for companies that do not necessarily trust each other completely to have a protected space where they can do joint computation on virtually shared data. So what is this about? What does it help? So here are a couple of use cases that we have in mind. So one is virtual data pooling. So that's exactly what I described before, right? Everybody has its secrets and they want to compute together something on top of that. Another use case is secrets management. So this is actually deployed already in production by a lot of, not based on Carbyne Stack, but in general by a large number of companies where they kind of split up credentials into these secrets and then do, for example, a signing operation or even a complete encryption based on that secret key without ever materializing the key in a single place. So in the end, you can have an encryption of a secret data set without any party ever seeing the encryption key. That's a little bit of magic and mind-boggling, but that's what secure multi-party computation can do for you. Private correlation, that's another use case. So we are here at a virus a company that creates virus scanners. So that's a use case, right? So you have multiple companies that do want to share insights about the vulnerabilities maybe that they have in their systems, but without exposing their infrastructure to the others, right? And that is what you can do. You can check, for example, what common software artifacts do these companies use, what are the threats associated, but without ever telling people this is exactly what I use. Still, you get at the end the result. There is a common threat to all of these companies, and please, let's find solutions for that. Collaborative learning, we heard about generative AI today already. So this is one step further where you have data sets that you want to use to train an AI system coming from different parties. And you do not want to expose the data to the other parties. And then you can even do training, although it's very expensive in that setting, to be honest, using secure multi-party computation as well. So now what's the difference between what we heard already today, confidential computing, and computing on encrypted data technologies that are here? So it's very chorused comparison, right? So you can discuss every single entry here, but on a high level, there might be some truth in it. So for confidential computing, the overheads are typically very small. For computing encrypted data, they are significant in different ways. So for secure multi-party computation, you have significant communication overhead because these guys have to talk all the time to each other. For homomorphic encryption, you have a lot of computation overhead because the operations that you do are heavyweight cryptographic primitives that are super expensive to execute. Trusted compute base, so for confidential computing, it can be significant, right? You have to trust the hardware, the software stack, and so on and so forth. For computing encrypted data technologies, it's rather small, and you can patch it easily because it's software only, right? Security, for confidential computing, I call it protected in use because while it's protected in memory, it's still computed in the clear when on the CPU. That's not the case for computing encrypted data technologies because, yeah, they work literally on the encrypted data without decrypting it. Security assumption for confidential computing, correctness of hardware. Implementation for secure multi-party computation. The idea is that these different parties involved, they should not collude. If they do, they can reconstruct the secrets and the security is broken. For homomorphic encryption, it's the secrecy of keys. Confidential computing has the benefit that you can protect code and data during computation. That's not the case for secure multi-party computation because all the parties do the same, right? So there is no way of hiding what they actually do. Ease of use, also a big plus for confidential computing. So as of today, you can just lift and shift, right? There is no much effort involved in this anymore. For secure multi-party computation and homomorphic encryption, it's a lot of effort. You have to basically rewrite your complete program for these kind of architectures to make it work. So conclusion, what are the sweet spots for these technologies? Whenever you have high performance and efficiency requirements, also low cost is key, then go for confidential computing. If we have very highly sensitive data or have very strict legal requirements, then computing on encrypted data might be a good choice. Secure multi-party computation, if it's multiple parties. Homomorphic encryption, if you are rather thinking about just offloading the computation to another party. So what is our vision? We want to allow you to build MPC-based system in the same way as you build regular applications. And that means kind of we have to address the DevOps cycle here. What is already covered quite good is the left side. So there are languages, there are compilers, there are runtimes for secure multi-party computation, but what is not there as of today is the ops part, right? How to deploy it, how to operate it, how to monitor it. And there is the idea to come up with MPC as a service. And the idea is that we provide with Carbyne Stack all these nice properties that you have when you use cloud-native technologies for your regular workloads and apply this in the same way to Carbyne Stack and give you all these nice properties. So what does this concretely mean? So what we do in Carbyne Stack, it's all based on Kubernetes. We use Knative as the function as a service framework that is, again, using Istio for doing all the network stuff. We have a distributed system, as I said, so we have to coordinate among the different clusters during computation, and that means we have a single source of truth, which is implemented using etcd, also across, not only inside the clusters, but also across the clusters. This gives us all the scalability requirements that you get from the scalability properties that you get from using Kubernetes and these other technologies. Second question, is MPC the answer to everything? No, it is not. The best way ahead from our point of view is to combine different technologies, for example, confidential computing and secure multi-party computation. And Otto actually gave a nice talk last week on our Carbyne Stack community conference about how this could be done. So he demonstrated how Carbyne Stack can be deployed in Constellation and getting the nice properties from Constellation and combine them with the very high security guarantees from Carbyne Stack. Another way that we use confidential computing is for improving efficiency. So you have seen this fancy slide about a multiplication, and this is preparing what is required to do this multiplication. It's super expensive, and we came up recently with approaches that allow you to bring down this effort significantly, so that by combining these processes with confidential computing, you can bring down the costs by orders of magnitude, which is quite nice. Also, there is a trade-off then also in terms of security, because it's no longer rooted explicitly or completely in cryptography, but also in trust in hardware. But anyway, it gives you kind of a little bit of a spectrum for tuning security against performance. Then we need to make sure, of course, because people bring in their data into this system and trust in the capability of the platform to protect the data. And then, of course, authentication and authorization plays a very central role here. We use Open Policy Agent and ORI Kratos and ORI Hydra for implementing authentication and authorization. So that gives us the chance to say the result of that computation should be accessible only to this and that participant in the system, which is very essential. And if you look at the solutions that are out there already for MPC, they always come up with some custom implementation for authorization at least. And we decided to go more a standard way and use established technologies. Also of course, with the thinking in the background that we don't want to reinvent the wheel if there is something available that can be just reused. Okay, observability, I will skip that. More interesting is we have to deploy Carbyne Stack, which is already now a very complex system. And if you look at our website, the steps to do this manually is, I don't know, 20 plus steps until you have a running system. And that kind of cries for an automation strategy. And we have recently come up with our first implementation to do that using Terraform and CDKTF. So these 20 steps that are required to set it up kind of are melt down into a single invocation of CDKTF deploy, and then you are done. So this is available for Azure for local kind deployment, and we will also address other public clouds in the future. We have heard about operators today already. That's also very interesting for us, and we use it already for one of our services where we implemented a Kubernetes native way of doing things, where we represent our domain objects really like as custom resources, which is very nice because I think it was mentioned also in the last talk. You give DevOps people the chance to work with the system with the tools they know, right? And that's a good thing. We also use it for other things like establishing this virtual cloud that I talked before with that key in the middle. Setting this up is a very complex multi-step process, and we are currently designing a service that is also heavily based on custom resources and an operator to automate this setup process. Then, how much time do I have still? 5 minutes, okay. Then just quickly, cost efficiency is something that I said is very important. If you look at the price models of public clouds, you see that egress traffic is super expensive, right? Ingress is cheap. They are happy if you push your data on their systems, but they are not so happy if there is something going out again. That is reflected in the pricing model. For MPC, this is a problem because these guys have to communicate all the time. So you always have egress traffic and a lot of it, and that creates crazy costs when deploying on public clouds. And that's the reason why we are investing very much resources into research to bring this cost down. And there are approaches that allow you to bring that down by 3 orders of magnitude, the cost. So instead of paying 1,000 euro for solving a certain problems, you suddenly pay only €1, which is a huge difference that also qualifies computing on encrypted data systems for more use cases. And then, of course, we want to also provide higher level services, not only storing and computing, but also higher level services for data analytics and federated learning. So you will find on our website, in our GitHub repository, also an experimental implementation of federated learning that uses Carbyne Stack for doing the aggregation of the model updates in the backend, which makes federated learning an actual secure way of doing distributed learning, and is a very nice showcase application for Carbyne Stack. So Carbyne Stack is open source. I said it already. I think you have understood that what we do is a major effort, and that's the reason why we said we want to do this together with others. So here you see with this open source onion a couple of companies that have contributed already to Carbyne Stack. We have more and more users that integrate their solutions with Carbyne Stack and provide additional security guarantees for their systems. And I, unfortunately, because I have not the permission to, but we are in discussion with several hyperscalers to adopt this. Maybe you have seen I can say that on AWS they have the first live service with MPC in production. It's a digital clean room, and not saying that we are talking with AWS, but we are talking with hyperscalers, whether Carbyne Stack could be a way of deploying these kind of MPC systems more efficiently on their clouds. And then we have different ways of engaging with the community. So we have, of course, the GitHub repository. We have a website where we communicate documentation and also events around Carbyne Stack. We have recently started a Medium blog. So together with Otto, I also described there this thing that I mentioned, combining Constellation and Carbyne Stack to create an even more secure system. We have a LinkedIn feed that you are invited to follow to see what's going on. And finally, I'm not sure, to be honest, how many people are really into privacy enhancing technologies in this group, but if you are interested, show us your love by giving us a star on GitHub. You can, of course, we are very happy if you share the story about Carbyne Stack, even maybe you want to contribute to that. And then one thing, if you want to learn more about Carbyne Stack, we have once a year the Carbyne StackCon, which is a gathering of the community around Carbyne Stack, where we give more in-depth insights about plans and current status of Carbyne Stack. You are very welcome to attend this as well, of course. It just happened 1 week ago, so we have to wait another year now, but anyway, heads up already. Okay, thank you, that's it.